Hello, everyone. My name's Martin Drager. I'm with Water Services and Technologies here in Canada. And I'm here with Dr. Grant Carey with Pour Water Solutions, who will be presenting today's webinar. Today's webinar is entitled Unravelling PFAS Origins, Forensic Techniques with Radial and Stack Bar Visualization. Just a little bit about Grant. Grant is the president of Pour Water Solutions and has more than 30 years of experience focusing on the characterization and remediation of hundreds of impacted sites. Grant specializes in PFAS, fate and remediation, environmental forensics, groundwater modeling and visualization, and he's also involved with a number of CERDIP and ESTCP projects with focus on PFAS in situ remediation modeling and visualization. Grant's also an adjunct research professor at Carleton University in Ottawa, Canada, and an adjunct professor at the University of Toronto. Thanks for joining us, Grant. We're really excited to learn more about PFAS and the origins and how we look at these contaminants in different ways. Okay, so before we get into the presentation, I just wanted to go through a couple of things. First, we are taking questions throughout the webinar. If you look at the chat window, just put your question in there. We'll definitely get to it before the end of the webinar, but we are taking questions at the end. And you'll also notice a few polls that you'll be seeing on your screen. We'd really appreciate it if you could contribute to those polls. It will help us improve our webinar and the content that we deliver. So this is just a reminder, this is the third in a four-part series for PFAS webinars. The next one is in October 21st, and it's using visual PFAS to evaluate vadose zone sources. So in terms of the actual agenda, we're going to do a quick overview of water services and technologies while we're doing this. Grant will go into the AFFF, product differentiation, PFAS visualization case studies, and then we'll go into conclusions and recommendations and open the floor for questions and address those. So a little bit about water services and technologies. So we formed our company in 2017 in Brazil. Dr. Nielsen Giger, some of you may be familiar with his name. He's the author of one of the most popular modeling codes, Visual ModFlow, for contaminant transport and flow modeling. He also authored FlowPath 2, which was the United Kingdom Environmental Agency's standard for particle tracking. He also developed a number of other codes that have become popular over the years and was the basic founder or the visionary behind HydroGeoAnalyst, which today is a very popular environmental data management, analysis, and visualization tool. Our company really focuses on water resources management and site characterization. And one of the reasons we really enjoy and have brought visual PFAS into our fold is the power of the software that this brings to our projects. In terms of our projects, we do focus a lot in mining, but we do offer technical services for public and private sector clients. We specialize in hydrogeology, hydrology, and aqueous geochemistry. And our big part of our business is environmental data management and reporting. So we have the technical services technology, and we do training courses. Similar to this webinar, we offer courses on fee flow, visual mod flow, pumping test data analysis, data management to help clients and those who are looking for more information in the environmental sector improve the process that they go through and how they deliver projects to their clients. Currently, we have offices in Kazakhstan and Canada as well, mostly because of our mining connections, but we're continually expanding globally. We really hope that you enjoy this webinar. I know that the content that Grant's put together is exceptional and will be very useful as you tackle your PFAS projects. So Grant, feel free to take the floor.
Thanks, Martin. And good afternoon, everybody. Thanks very much for good afternoon, good morning to some. Thanks for coming out today. We really appreciate you taking the time to join us. We move to the next slide here. So one thing I wanted to mention before I begin, I am going to cover a lot of different topics and case studies today. I know it's a lot of information, so if you'd like a copy of the slides after I'm finished, please feel free to send me an email, gcarey@poorwater.com, and I'd be happy to send you the PowerPoint or any papers that I'm talking about during the presentation. So we're here today to talk about PFAS forensics. And I think the most common way of looking at forensics is talking about how we can characterize and differentiate between multiple sources that may be contributing to a PFAS plume. That's the most conventional way of thinking about PFAS forensics. And the key thing with forensics, as a lot of you know, is you really need technically sound and convincing conceptual site models to back up whatever your multiple lines of evidence are showing. And this is actually, forensics is really, to me, a lot like site characterization and remediation. A lot of the things we look at with characterizing a site or looking at remediation data are pretty similar to the types of trends we look at with this kind of a more specific forensic analysis. So over the last year or so, I've been involved with an NGWA expert committee that's developing a white paper talking about PFAS forensic methods, because it is a very opportune time to talk about that these days. As you can see on the bottom of the slide, there's a lot of different ways we can look at forensics. We can look at visual methods, we can look at statistics. A lot of work's being done in these areas. And my contribution to the white paper is more about simple visualization methods like radial diagrams and stack bars on maps, and the types of trends we can actually look at and demonstrate with those visual methods. So that's what we're going to talk about today, is specifically about radial diagram maps and stack bar maps and how these can actually support a forensic analysis. And in terms of what do we use these methods for? So a simple thing, let's say you've got a couple different source areas. You want to look to see where you have exceedances of PFAS of concern. Where do you have non-detects? That helps to show maybe a distinction between source contributions to a plume. So anytime you're visualizing something, you want to be able to show where you have the exceedances and non-detect symbols. A lot of times we look for, whether it's forensics or site characterization, what's the relative concentration of short versus long chain PFAS? How does it change in a plume downgradient of one or several source areas? And then what are lines of evidence for precursor degradation? Can we see it happening when we look at the data? And with PFAS transport and plumes, the PFAS of concern tend not to biodegrade naturally. There may be attenuation through absorption into silts and clays, which can reduce plume concentrations and things like that. So that's something we look for. Obviously, we look for site versus background. Is there something coming into the site that explains PFAS concentrations, top assay results, and then looking at how things change over time and space on the same plot. That can be really valuable to be able to do that. So before we talk about visualization case studies, let's talk about the different types of AFFF products and what are the characteristics of the products and actually of the PFAS we see in soil and groundwater after releases of these different AFFF products. That helps to create clues on what we want to look for if we're trying to differentiate between different source areas, for example, at a larger site, or between different sources at multiple sites. And this discussion, so I'm focusing on AFFF sites because the case studies we're showing are mainly AFFF sites, but the same thing applies to different types of PFAS products. They have certain manufacturing processes which can create quite different visual signatures between different sources. So before I get into the products, I wanted to talk just a little bit about common terminology, make sure we're all on the same page about what terms mean. So PFAS, perfluoroalkyl acids, those are really where the PFAS of concern typically come from, the regulated PFAS. And those are broken down into two buckets, sulfonates on the left, which I also call PFSAs, and carboxylates or PFCAs. The sulfonates are the chemicals that end with S, like PFOS, PFOS. And the carboxylates are the chemicals that end with A, like PFOA. So very simple, nice categories. And then we add into that precursors. So precursors are called precursors because they're basically parent species that may degrade either naturally or maybe through enhanced remediation at a site. They may degrade to PFAS. So if precursors are degrading to regulated PFAS of concern. That's definitely something we want to look out for. And there are really two types of precursors that we talk about. There's ECF-based. ECF is really talking about electrochemical fluorination as a manufacturing process. That creates a certain type of precursors, and those tend to degrade to sulfonates. And then the FT-based precursors are produced through fluorotelomerization, and those precursors tend to biodegrade to carboxylates. So now we're starting to see different types of processes that can create different signatures between different source areas. There's a fifth category, PFEAs, perfluoroether acids. I'm not going to talk that much about those today. With AFFF sites, they're not as much a concern. These are typically replacement products like HFPODA, which is a Gen X class. But today we're really going to talk mainly about the two types of PFAAs and precursors. And for anyone who wants, took me a while to get this down. There's, with EPA method 1633, there's 40 analytes. We get results back in reports from labs. So this just breaks it down into different categories. You can see which of the precursors degrade to PFAS in this case, and which degrade to carboxylates from method 1633. So it's just here of interest if anybody wants a copy of this. So in terms of AFFF products, there was some great work done by Dr. Jennifer Field, Dr. David Sedlak, Dr. Lisa Alvarez-Cohen back in about 2017. They published a report as part of a CERTA project. And what they did is they analyzed the composition of the raw AFFF products, both produced with electrochemical fluorination is one process, or with fluorotelomerization. So I'm just going to show you what they found in terms of what does the composition of the actual raw AFFF products look like, and what does that tell us about what we expect to see in soil and groundwater when these different products get released. So with this report, I'm just using a radial diagram to plot the data that they had in the report. And we can see with ECF-based AFFF products, PFAS is by far the highest concentration. That's going to be over several thousand milligram per liter in the raw AFFF. And you can see PFHXS is also high, but typically that's maybe 10 to 20% of PFAS in the raw product. And then all the other compounds, all the carboxylates are very low compared to these sulfonates. PFOA might be 1% of PFAS, for example, because it's present as an impurity. But these are really sulfonate-focused. It's a sulfonate-focused product. And then in addition to the PFAAs, the ECF-based AFFF products also have a lot of precursors. And you can see starting in about 1989, 1990, the precursors were heavily weighted towards what we call C6 precursors. Those are precursors that have 6 carbons in them. And those can actually break down to compounds like PFHXS. So these are sulfonate-based precursors. They'll degrade if they're C6, typically to PFHXS. And so that's why even though PFAS is much higher in ECF-based AFFF than the other compounds, we tend to sometimes see PFHXS even at higher concentrations in groundwater because a lot of these precursors that are C6 precursors have biodegraded to PFHXS. So a lot of AFFF sites, if you have high concentrations of PFAS and PFHXS, then you know a fair bit of ECF-based AFFF products were used at that site. So now the other type of AFFF products. One manufacturer used the ECF-based product process to produce AFFF. All the other manufacturers use the fluorotelmer-based process. And that's really the composition of fluorotelmer AFFF is really fluorotelmers. It's actually got low concentrations of like 6,2-FTS, for example, in the raw product. But we do tend to see high concentrations of 6,2-FTS where these products have been used in soil and groundwater. And that's because there are a lot of parent products of 6,2-FTS in the raw AFFF that biodegrade to 6,2-FTS, and that can further biodegrade to some of the PFAAs. We'll talk about the pathways in a little bit. So the key thing with this product is they don't actually have PFAAs detected in these raw products. It's really just the fluorotelmer precursors that are in these products. but we know biodegradation is happening when the AFFF gets in the ground because of what we're seeing in soil and groundwater. So the bottom line, if you had let's say a fire training area and they only used ECF-based AFFF, you'd have high concentrations of PFAS, PFHXS, some PFOA, and some of the other carboxylates, much lower though. And you wouldn't see the 6,2-FTS, for example. But a lot of sites, they tended to use a mixture of products. I've seen a few sites which are very distinct signatures. Only one or the other products were used, ECF or fluorotelmer based, but that's pretty rare. A lot of fire training areas, they tended to use different products over time. So you might see a mixture of impacts from each product. So with the FT-based AFFF products, when those are released into the ground, we obviously see high A2S FTS sometimes, typically high 6.2 FTS. I've seen pretty low 4.2 FTS. I haven't seen that very high at most sites. And we see the high carboxylates, PFOA down to PFBA. PFNA is typically pretty low at these AFFF sites compared to PFOA. So we're starting to see that there are actually clues we can look for. If we want to see, let's say there's a source area, and we're going to talk about a case study where we actually have 12 source areas that are known. We wanted to evaluate, can we use visualization methods to actually distinguish which product was predominantly used in any of those source areas. We weren't sure if that would be the case, but we got some interesting results, so I'll share those with you in a little bit. But the key clues we're looking for, one is what's the relative ratio of, say, total sulfonates versus total carboxylates. That'll tell us whether it's an ECF or an FT-based AFFF product that was predominantly used. And also, if FT products have been used, what's the relative concentration of long chain versus short chain carboxylates? Because the older FT-based products tended to have longer chain compounds in them, longer chain precursors. And the modern FT products really are more focused. They were replacement using just short chain. So if you see a mix of long and short chain compounds from fluorotelmer, then you know you had the older products being used. If it's really focused on the short chains almost entirely, downgradient of an AFFF area with FT daughter products, so we know that was probably a modern FT product. So I'm going to talk a little bit about a case study, and I've gone through this case study in detail on a prior webinar. I'm going to go through just select sections of it because talking about more from a forensic opportunity for looking at different trends and what we get from these from the data from the site. This was a great site to work with. It's Ellsworth Air Force Base, which is in South Dakota. And I just wanted to acknowledge our co-authors on this paper that we published this year. And if anybody wants a copy of the paper, just send me an email and I'll happily send it to you. So Rita Krebs is the remedial project manager for Ellsworth Air Force Base with the Air Force Civil Engineer Center. She was really helpful in providing us with the data, providing what we needed to know the history of behind different areas at the site. Jeremiah Duncan with GZA was also very helpful with evaluating the data. And then you can see we've got Gabe Carey, Mia, Jillian, and Kira as well, all helping with evaluating the data through an intensive visualization research project last year. And I just wanted to mention Gabe Carey, who's also my son, is a developer of Visual PFAS. He's the one who developed the program that we use to actually map these radial diagrams and stack bars. So as I mentioned before, at this site, they actually had we'll call it 12 AFFF source areas that were known that are listed here, AFFF 1 through 12. There's also at the bottom a former fire training area, OU1. And I'm actually going to share results first from the site inspection, which was only done in these AFFF areas. So I'll talk a little bit later about some of the data from the OU1, the former fire training area. And then we'll talk about some other data from the remedial investigation, which was even a more comprehensive data set. So lots of great data to work with this site. And when I show some radial diagram and stack bar maps, I'm going to zoom in on 3 AFFF source areas. There's AFFF1, which you'll see in the middle, sort of bottom of the figure. That's the current fire training area, and it's directly adjacent to the former fire training area. And then we've got AFFF-8, which is where a crash had happened with AFFF used in response back in 2008. And then AFFF-12 is a former building with some interesting characteristics. And what we're doing is we're looking at, okay, what are the different products that might have been used in those three source areas? We're just going to focus on those for now. And of course, I think photographs go a long way to helping us understand former fire training practices in the past. This is a photograph that Rita Krebs had sent recently. I thought really displays, how these former fire training areas were used. This is showing the former burn pit. We've got an old plane that's been put on fire. The fire's been put out many times. You can see here the former burn pit wasn't lined, and there are impacts that we've seen below ground. And then on the right side, I thought this is interesting. This is a recent aerial photo, and it's showing the former burn pit area. That orange outline is the burn pit that we see on the right in the middle of the photograph. And you can see the current fire training area, which was built in 1990 and has been used since 1990, very different. You've got the concrete liner, also included concrete liner below the burn pit area. So back in 1990, DoD recognized that there were releases occurring of chlorinated solvents and hydrocarbons from these unlined burn pits used historically. So they went through and stopped using the old ones, built all the new ones. So it's just an interesting picture to contrast the difference in how these burn pits were set up. So I'm going to show first a radial diagram map, and I wanted to talk about this is grouped in a certain way that helps you evaluate different types of trends for different groups of chemicals. So the first thing you'll see is the three axes at the top of the radial diagram. Those are all sulfonates that end in S: PFAS, PFHXS, PFBS. And then the six axes on the bottom, those are the carboxylates, ranging from the short chain PFBA all the way up to PFNA. And you'll see we've actually ordered the species on the diagram. So the long chain species are all on the left side, and the short chain compounds are all on the right side. So now, for example, if you look at that orange data series with the blue line around it, you can see that the long chain compounds are all pretty low concentration at this particular source area. This is AFFF-12, one of the source areas we're looking at. And if you look on the right side, we've got higher concentrations of the short chain compounds. So automatically, just visually, by looking at the left versus the right, we can actually see which side is high, which side is low. So it's just a nice, simple way to start looking at not just trends for each axis on its own, but for groups of chemicals. We can look at top versus bottom, or we can look at left versus right to look at these different groups. And usually with radial diagrams, I like to plot at least two data series. So the one on the outside, that's the site-wide maximum from the site inspection that was done about 5 or 6 years ago. That's across all source zones. And then the blue outline, that's the source area maximum at AFFF-12. That's the well that had the highest concentrations of PFAS and PFOA in this case. So that's what we do. And I wanted to mention you can see concentrations at this site do range by up to 5 orders of magnitude. So we're using a log scale for this particular site. And we're also making every axis has the same range from 0.01 microgram per liter up to 1,000. Even though if you look at PFNA, there was nothing above 10. But I actually use the same range for all axes, so I can actually look at a map and visually see right away where each chemical might be high or low compared to the others at the same location. So there's different ways of setting these up. Sometimes you might want arithmetic axes or scales, sometimes different ranges for different chemicals. In this case, we're looking at log scale. And the nice thing about log scale is each pair of tick marks represents an order of magnitude change in concentration on an axis. So if you look at the PFAS axis at the top left, you can actually see the site maximum is 100, and you can see there's 2 tick marks between that and the maximum at AFFF-12, which is about 1. So just visually, I don't even need to look at the numbers. I can see with the 2 tick marks, there's a 2 order of magnitude difference between the site maximum and the maximum at this actual source area. So a lot of what I do with radial diagrams is I'm counting the tick marks to count orders of magnitude changes between chemicals at one location or along a flow path. You can actually see how things are declining in terms of orders of magnitude. And you'll also see here we're showing exceedance symbols. We're also plotting non-detects where they show up on the map. This particular source area didn't have any non-detects in the maximum concentrations. All species were detected. And this just basically is another layer of information we can put on a radial diagram map. It's free. It doesn't take up extra space, but sometimes that can be really vital for showing extra things in a map. And that's a lot of what I try to do is maximize what we can show on a single figure to maximize what we get out of it. So just plotting the map now, if you look at AFFF-1, that's in the middle of the site near the bottom of the base, and you can see the source area concentrations line up with the maximum for the site. So this is where the maximum concentrations have been measured. I can see instantly looking at the map where the highest concentrations are. And that's one value of looking at radial diagrams. We can plot, in this case, 9 PFAS species on a single map and see where things are high and low, just to get a bird's eye view of how things vary across the different source areas. And then if we talked about AFFF-12 at the top, we can see how on the left side, it's even more clear. The left side is small. The right side is quite large, more tick marks, higher concentrations. And that's something we'll show a little bit more what that looks like with stack bar fingerprints. But that's telling us, okay, definitely more short chains, at least for the carboxylates, than there are long chains like PFOA. And then just looking at the bottom, we see AFFF-8. That was the 2006 crash response site. And you can see a lot of non-detect symbols, really not much detected there, just a few species, which is good. So it shows that not much got in the ground from responding to that crash. Okay, so now let's transition to stack bars. And this is really all about proportion. Radial diagrams are about showing magnitude and how magnitude changes across a site. Stack bars are really about, it's like pie charts, showing proportion. One thing I like about stack bars versus pie charts is we can actually have tick marks to show the scale on the left side of the bar, like we see here from 0 to 100%. So I can very quickly tell you total sulfonates are 70% just by looking at where the interface between the blue and the orange lines line up with that scale. And that, when you put those tick marks on the base map, that really helps to see you can get more precise proportions at each location with those tick marks. And I also like the bars because sometimes they put short chains on the bottom, long chains on the top of the bar, and it's just kind of a linear. It's more intuitive to see that linearly versus a pie chart where I always struggle to remember which was the first pie, first piece of that pie was short chain. So, okay, so now we're looking at total sulfonates in the orange versus total carboxylates in blue. And looking at the percentages of those totals doesn't tell us what was the percent of ECF versus FT-based AFFF products used in the source area. Because the AFFF products actually have a lot of precursors we're not looking at with this analysis, but it does give us a pretty good qualitative view of, okay, well, which of those two types, FT or ECF, were predominantly used in the source area? It's qualitatively, it can give us some information about that. So you can see at AFFF-1, the sulfonates, total sulfonates are a little over 60%, 65% of the combined carboxylates and sulfonates. So that's telling us, yeah, okay, more sulfonates there, probably more ECF-based product, but you'd have to do a more sophisticated mass balance to confirm that. And then AFFF-12, it's a little different. Now we're actually down like 40% sulfonates, 60% carboxylates. So that's looking like that was actually more FT-based product might have been used there than the ECF AFFF. And then AFFF-8 near the bottom, there were only 2 compounds detected, but you can see they were clearly mainly the carboxylates. And one thing I wanted to mention with stack bar maps, this is about adding more layers of information. You can see how I've actually got total concentrations, sulfonates plus carboxylates in microgram per liter, shown in brackets above each bar. So AFFF-12 has a total of 17 microgram per liter. The the current fire training area, AFFF-1, has 240. So that's one way that I actually get magnitudes onto a stacked bar map. So we're not just looking at proportions. Adding the total concentrations actually adds a magnitude dimension to it, which is helpful. And then finally, for this example, I wanted to show short chain versus long chain carboxylates. This is really about where FT products were used, AFFF. Was it more the modern FT, which is almost all short chain, or is it more the legacy FT, which might be a mixture of the two? And we can see in this example, this is from the current fire training area, and we can see the short chains are close to 80%. But we still have about 20% long chains used. So definitely a mixture of the two different products. But current fire training area, some of this contamination that's there probably came from the former fire training area next to it, which has a lot of 6.2 FTS mixed in with 8.2 FTS. But it does start when we put these on a map. Now you look at AFFF-12, you can see, well, the green are the short chains. And you can see I've used all green for all short chains, and then yellow to red for the long chains. So just visually, I can look at AFFF-12. I can see greens represent 95% of the long plus short chains there. And that's telling me, okay, they probably used a lot more modern FT-based product than the legacy FT product there. And you can see most of the others in the middle of the base. The long chains might have 40%, 20%, so probably more of a mixture. But if you had a site that only had, and I've seen some sites that only had FT-based products and where there's only carboxylates present, sulfonates are almost non-detect, you can start to see differences just by plotting short versus long chain or the sulfonates versus carboxylates between different source areas. That could be a really helpful way to distinguish between contributions. Okay, so I'm going to talk about ratios because sometimes we look at ratios, maybe sulfonates versus carboxylates. In this case, we can use ratios as lines of evidence for whether transformation of precursors to PFAS is occurring along a flow path. And that might be important because when we're looking at source contributions, we have to keep in mind that plume's downgradient of each source may have some PFAS getting produced along the flow path. So we want to evaluate evidence. Is that occurring? Does that affect our analysis of contributions? So we can use ratios for that. And in terms of 6.2 FTS, probably the most common precursor I've seen at AFFF-impacted sites. And there's actually 3 daughter products. The PFHXA is produced with the highest yield. PFPEA is produced with a little bit less yield, but also fairly high. And then to a lesser extent, PFBA is produced. All 3 of those are produced during the biodegradation of 6.2 FTS. So if you look at ratios, we can put the parent, that's the precursor concentration, on the top part of the ratio, and we can put one of the daughter product concentrations on the bottom part of the ratio. So this journal paper that we had published had a detailed explanation looking at these ratios and how they change between the source area. And there's an area at the former fire training area where oxygen was injected about 10 or 15 years ago. And that was for a hydrocarbon remedy. That's what we do with hydrocarbons. We inject oxygen to enhance aerobic bioremediation of the hydrocarbons. But a lot of these, so 6.2 FTS and a lot of other precursors, they degrade typically only under aerobic conditions, or at least most quickly under aerobic conditions. Very few actually biodegrade under anaerobic conditions. So if you're injecting oxygen, say at a site to enhance degradation of hydrocarbons, at this site, there was a classic paper by McGuire et al. From 2014 that showed the oxygen injection stimulated the biodegradation of the precursor. Actually, a different precursor is what they looked at, to the daughter products. So in this case, this one radial diagram has 3 axes, one for each daughter product, and this ratio of parent to each of the daughter products. And in the source area, the ratio is about 1 for all 3 axes. That's that dashed line. And in a downgrading area near where oxygen was injected, to enhance hydrocarbon degradation. That's the blue data series. And you can see downgradient at the source of the source. PFHXA is dropped by close to 1.5 orders of magnitude. PFPEA dropped by about an order of magnitude, and PFBA by about half an order of magnitude. And those proportional changes are consistent with what you'd expect when 6,2-FTS is biodegrading to the 3 different daughter products. So the one thing to think about, though, is if you're looking at these ratios, you also have to ask yourselves, because the precursors tend to absorb more strongly than the daughter products, at least 6,2-FTS will. If you're in a part of the plume where things are not stable, and you've got an expanding plume of precursors, say, then this ratio also goes down just because of differential absorption. And sometimes I have people looking at ratios, and a lot of people say, well, the ratio is different because of differential absorption. And that's true at sites where the plume is not stable. But I'm going to show a modeling example where if the plume is stable, differential absorption actually is not a factor and will not influence these ratios. So let's just look at a simple hypothetical. Let's say we've got a release of 2 chemicals with different absorption coefficients, 6,2-FTS and PFHXA. Let's say the release is the same extent in this red source zone, 10 microgram per liter of each chemical released at the same time. The only difference is the retardation coefficient. Groundwater velocity in this model is 100 feet per year. And we know that the velocity of the PFAS plumes are going to be equal to the velocity of groundwater divided by the retardation coefficient. So just using some simple numbers, let's assume 6,2-FTS has a KLC 10 times higher than PFHXA. Let's assume FOC is 0.1%. So we calculate 6,2-FTS, the plume is actually moving 3 times more slowly than PFHXA. So when you model them, and you model the releases starting at the same time, same source concentrations, we see PFHXA has gone a lot further because it doesn't absorb very much compared to 6,2-FTS. And the retardation has held back that 6,2-FTS plume. But if you look at, let's say we look at this distance of 500 feet across both plumes. On the left side of that dotted line, the plumes actually look really similar. And that's because on the left side, conditions are at steady state. It's a couple hundred feet down gradient of the source area. Things do reach steady state after a while. And once things are at steady state and the plumes are stable, then the different absorption coefficients make 0 difference in what the plumes look like. They don't affect the extent of the plume when you're in a portion where the plume is stable. It's only in the downgradient areas where the plumes aren't stable. You've got 6,2-FTS still expanding on the right side of that dotted line, then differential absorption applies. And if we looked at that ratio, we would see it declining because of differential absorption. But on the left side of that dotted line, there is no effect from differential absorption because retardation does not affect the plumes at steady state or stable plumes. And then if the ratio is declining, we know it's because of biodegradation. So that's something you need to look at if you want to actually use that ratio as a line of evidence for biotransformation. And then thank you, Rita, for all the data. You can see I really like to use your site because it's a great example. So this is also Ellsworth Air Force Base, and this is the remedial investigation data set. We can see a lot of sample points. And at each well where they took PFAS samples, I calculated what the ratio was of the precursor, 6,2-FTS, to the daughter product, PFHXA. And the dark red is greater than 1. The orange is 0.3 to 1. And the orange or red are where you've got a fair bit of precursor there relative to the amount of PFHXA. Doesn't tell us what the magnitudes are, but it tells us in a relative sense, there's a fair bit of precursor where we have orange or red locations. And as you get lighter in color, yellows to blues to whites, well, then the precursor is getting smaller and smaller compared to the daughter product. And that could be evidence of biodegradation as long as differential absorption doesn't apply. So I've done a detailed analysis, which I don't have time to show you. I've actually gone and looked at concentrations of 6,2-FTS and PFHXA in each of these areas. And I can confirm that where we've got the gray zone near AFFF-4, which is a former fire station, you can see at the former fire station, lots of orange and red. So a lot of precursor at AFFF-4. But then when you look down gradient, groundwater is flowing in the direction of the purple arrows, we see colors are changing. And that ratio is getting smaller, going from orange to yellow to blue. And that, when I look at the concentrations of each compound, I see the precursor getting smaller. I actually see increases in the daughter product, PFHXA. So I know and I know that this is close enough to AFFF-4, differential absorption doesn't apply in that part of the plume. So that's an area where we know from this ratio that biodegradation is occurring. And same with AFFF-1, the gray zone shown near the middle of the figure. That's also where the north part of that gray zone is where oxygen had been injected. And that's why we're seeing oranges changing to yellows and blues. A little bit further down gradient, we've got oranges on the property line. So higher precursor, yellows further down gradient, some distance down gradient. That could be biodegradation. It kind of looks like it, but it's far enough away. It could also be differential absorption. So that's where you'd want to look at 6.2 FTS over time and see, do you have stable concentrations? And I haven't done that yet. I'm not sure we have enough data yet to do that. But that's the kind of thing you have to look for if you want to use this as a line of evidence for biodegradation. All right, so thanks for hanging in. I've got one more kind of detailed case study and then a few quick examples of different sites, different methods. This is a study where I wanted to look at a couple things. I wanted to see, can we tell if we have different groundwater signatures entering a surface water pond? The blue box at this site, this is a Michigan Air Force base. They took some pore water samples, which are shown in the green symbols, surface water samples shown in the orange symbols, and I focused on that area shown with the blue outline. And there's also a groundwater well, which I'll show you close by. This area is down gradient of a former fire training area. So I wanted to try and better understand some of the dynamics between the different matrices and how signatures might change. So we can see we've got one groundwater well with a sample directly next to, or pretty close to where a pore water sample was collected, and that's within the sediments of this pond. And then we've got a surface water samples at different locations, mainly in the stream that receives the water coming from the pond. So we've got three different matrices. And one question I had when we started was, can we actually see evidence that PFAS and maybe PFHXS, which absorb fairly well to natural organic matter, do we see evidence that concentrations are declining between groundwater and pore water and maybe surface water because we've got enhanced absorption to organic rich sediments at the base of the pond? So do we see a differentiation between groundwater and pore water that shows that might be occurring? So this is the data from those locations I showed. Obviously, if all we had was the table, it's tough to work with. So thankfully, we have visualization methods now we can use. And one thing to point out, so stack bars, obviously, pie charts, great for chemical fingerprinting, nice proportion analysis. I actually think chemical fingerprinting is also looking at magnitude differences, concentration magnitudes. If you've got one source area with really high concentrations, another source area maybe with the same chemical signature, but much lower concentrations, you want to plot the relative concentrations of those sources versus what's in the downgradient plume to see, do you see evidence that of different contributions from each. So magnitudes can be a chemical fingerprint. Maybe we call it a magnitude fingerprint. So looking at the groundwater well location is MW13 shown in the inset map on the left. You can see it's fairly close to this pond and the surface water tributary coming off the pond. And we've got the highest, looking at the radial diagrams, I don't even have to go through what's on each axis. We can just see that the highest PFAA concentrations are in the shallow 2 to 7 foot depth below ground surface. And below that, concentrations drop by orders of magnitude. So that's just a nice magnitude fingerprint on where the PFAS are mainly coming from. Okay, so now let's look at the groundwater well MW13, and now we're looking at the proportional signature. And we've got pore water location number 1 shown nearby, and they actually look pretty similar. You do have a difference in sulfonates, where the sulfonates at MW13, the groundwater sample, sulfonates are about 60% of the total of these 9 compounds. And PW1, sulfonates are only 35%. And concentrations in pore water are a little bit less, about 30% lower than they were in the groundwater well. So that's telling us, well, maybe we are getting some differential absorption of the sulfonates in organic rich sediments. We'd have to look at concentrations over time. If they're stable, that's probably not happening. But if concentrations are changing over time, still increasing in the pore water, then we are maybe getting some segregation, and some of the sulfonates are absorbing more to the sediments before groundwater discharges. So now what's interesting is if you plot other pore water samples from the same pond, and now we've got a completely different chemical signature. The red is PFAS, and you can see looking at PW4 and just counting the tick marks, we can see PFAS is 80% of the total of all these chemicals at PW4. It's a little over 80% at PW5, about 65, 70% at PW3, about 90% at PW2. So it's high at all 4 of those locations. So that's telling us that groundwater discharging into the north part of the pond is a very different chemical signature. It's going to have a higher PFAS proportion than what we see at MW13. And maybe it's coming from the same source area. Maybe the source areas had multiple discharges in different places, but that's something to keep in mind. And then looking at PW6, that looks a little bit more like MW13, just without the PFAS. So this is one way to just try and distinguish where plumes coming from different sources might be contributing to a surface water feature. And then looking at surface water, so SW12D is surface water coming from the pond, going into a creek, taking it down gradient. And you can see PFAS is still pretty high. It's about 60%, but it's not the 80% or 90% we saw at the other pore water locations. And that's telling us we're probably getting some dilution in the pond. We're probably getting mixing of groundwater from the south end, mixing with groundwater coming from the north end. And that pond, what's coming out is a mixture of the two in surface water. And then as you go downstream, you can see the PFAS proportion is getting smaller, 50% at SW23D and only 20% at SW3D. And in fact, SW3D, the surface water sample, looks almost identical to MW13, the groundwater sample. So maybe what we're seeing is there's more groundwater like MW13 discharging into that stream, downgrading of the pond, or downstream, and maybe that's causing the water to look more like what we see at MW13. So just it's a nice example because it really shows visually how things change. So I know it's getting close to the end here, just a couple quick examples. This is a Navy site where a pilot test had been done to test how well plume stop, which is colloidal activated carbon, will absorb PFAS in a plume. So before the pilot test was done, the last webinar I did with Water Services and Technologies was actually on that remediation site. What was interesting is they did a pre-pilot test study. They did 3 soil borings, collected soil samples and groundwater samples at different depths, like we're seeing here in this cross section. You can see there's a few samples collected across the top near the water table at 3 different locations. Groundwater is flowing from left to right. And what we see, just looking at which of the PFAS that dominate at SB1, the top 3 samples, PFAS has the highest concentrations. And as you go down with depth, PFOA actually takes over and becomes the more dominant species. And I can just tell that just based on the transition from red dominating to blue dominating. So a nice simple visualization of that. And then if you look down gradient at SB2 and SB3, you can see other than the samples at the water table, the samples down gradient at SB2 and SB3 are pretty similar to what we see at SB1. So, which makes sense. Groundwater is flowing from left to right across the page. One thing that you also see at SB1A, that's the shallowest sample at SB1, is they actually have, compared to the other samples, fairly high proportion of C4 to C7 carboxylates, PFBA to PFHPA. The other samples don't have those, not in the same proportion. They're much lower in concentration at deeper sample intervals. So one question was, well, are we getting the precursors? There is a fair bit of 8.2 FTS and 6.2 FTS at that site in the shallow soil. At least there was at SB1 where there might have been a source present. So we're going to look at radial diagrams for the precursors, where the outer data series is the maximum over all the samples. The yellow is the sample result at each interval. And we can see at SB1A, well, we do. We have high concentrations of A2 FTS, which degrades to PFHPA, some to PFHXA. We've also got 6.2 FTS fairly high. So that could explain why we have the high precursors, the high C4 to C7 carboxylates at SB1A. But what's interesting is we also have high precursors at SB1B. But we didn't see the same proportion of C4 to C7 carboxylates there. They were much lower in SB1B. So it looks like the precursors aren't biodegrading. So adding on another layer of evidence, we can see adding oxygen data. Well, yeah, water table, we have high oxygen, 5.9 milligram per liter. That explains we are getting probably precursor biodegradation, explaining the C4 to C7 carboxylates. Deeper down, about 5 feet below the water table, oxygen's gone. We're not getting the degradation of the precursors. So now everything starts to make more sense. So it just shows multiple lines of evidence, layers of information can really help us better understand these sites. So I know I've just got a few more slides. I'll just go through these quickly in case they're helpful. So again, going back to Ellsworth Air Force Base, thank you, Rita. This is actually a pore water sampling study led by Hunter Anderson. Wood worked on this as well at the site. And all I'm showing are differences in concentration for the main PFAS measured in pore water below the former fire training area. And the dotted line is the maximum at all pore water samples anywhere in the former fire training area. This is one lysimeter where the blue data series represents shallow pore water concentrations. The black data series that's inside represents the deep pore water concentrations. And what you can see is the same thing. It's left side of the radial diagram are the long chains. The right side, those are the short chains. And you can see on the right side, we've got about an order of magnitude difference, one pair of tick marks between the shallow and the deep concentrations for pore water. On the left side, much bigger differences, 3 orders of magnitude differences for the long chains. And that makes sense because long chains absorb very strongly to the air-water interface in the vadose. So this is one way to visualize, okay, let's see if we can look for evidence of absorption to the air-water interface. That radial diagram to me says that's exactly what's happening and causing a lot of attenuation between the shallow and deep samples that were taken. And then looking, say, at lysimeter 104 and 106, we don't see the same thing. We actually see pretty consistent changes between shallow and deep for all long chain and short chain compounds. And that's because 104 and 106, the shallow samples were taken in clay. And I think here, it's not the absorption to the air-water interface driving the difference between shallow and deep. I think it's probably more limited water flow. And that's why they're all similar orders of magnitude depletion between shallow and deep at those two locations. So it's a lot of data, but plotting it this way visually, you have to play around a little bit to find something that works, can be really helpful for understanding these sites. And then if we want to look at things and how they change over time, which you need to do with pore water, this shows most of the modern events, very consistent results. The first event tended to be less. The blue-filled data series was lower in concentration than the other compounds, probably because of water injected during the installation of lysimeters. But after the first event, everything seemed to normalize and stayed pretty consistent. We talked about remediation. This is differential adsorption. All the sulfonates adsorb really well to the activated carbon. The plume stop installed at that Navy site I mentioned. Some of the shorter chain carboxylates didn't, and we don't expect them to, like PFBA, PFPEA, which aren't regulated, at least not with MCLs, and they have very high RSLs, residential screening levels. So this is another way of looking at differential adsorption. I've got a whole paper if you're interested looking at how we can use radial diagrams with a twist, a modification, to delineate the difference between aerobic, moderately anaerobic and strongly anaerobic redox zones. That tells us those are lines of evidence of where you have the most biodegradation of organics occurring, either through enhanced remediation or natural degradation. So let me know. I'm happy to send you that paper and some examples of sites. This works really, really well for delineating redox. So I think the biggest conclusion I can make after all this, I hope I made the point. Pictures are worth 1,000 words, literally. The visual aids, I find every time you do a technical analysis, it can be really hard to explain it to lay people. But if you have a picture that just shows it, it really helps. It can be very convincing. I do think radial diagrams and stack bar maps are certainly a place for them with visualizing PFAS trends. I think we need to look at other tools as well, but looking at magnitudes, chemical fingerprints, both methods very helpful. And then obviously we need multiple lines of evidence, hopefully all converging to the same conclusion. And if you hear that term differential absorption, you have to ask the question, is the plume stable or not? And that determines whether that applies. So Martin, I think I'll end that there if you want to take over.
Yeah, that's great. Thanks so much, Grant. Thanks for sharing your expertise on PFAS and also for providing a tool that can help with the characterization, visualization, reporting of the current situation at a site. Yeah, very, very helpful. One thing I'd like everyone to know is that Water Services and Technology does sell visual PFAS, and we are very happy to provide you with a live demo. Just go to our website. You'll see contact information there, or send an email directly through the invites that you're receiving for this webinar. I think that one of the things about our relationship with Grant is we've worked with Grant in Water Services and Technologies, and also in previous companies. And one of the things I can say emphatically is that he's onto something very, very good here. We have a lot of regulatory agencies demanding certain formats, and with PFAS coming on, not just in North America, Europe, around the world, there's going to be a high demand for this. So give some consideration. And also Grant's information is at the bottom of the screen here if you want to reach out to him directly. Now, we do have a couple questions, and I know time is ticking. So the first question we have is, with radial diagrams, when would you use different axis ranges for each PFAS based on actual min-max at a site instead of uniform concentration ranges for all axes?
That's a good question. And what I tend to do is if I'm looking at, let's say, attenuation along a flow path, the key question is, are PFAS declining in concentration between the source area and downgradient wells? Then you're not looking at one PFAS versus another at a location. You're looking at PFNA at the source versus PFNA at the next well, and then you would go to a chemical specific range and keep the maximum. If PFNA is lower in concentration than everything else, use a lower maximum, because the smaller the ranges, the easier the radial diagrams are to measure. So that's looking at attenuation along a flow path. I would definitely use chemical specific ranges there.
Okay, great. And another question, do you ever use arithmetic scale for radial diagram axes instead of log scale?
I do. Well, redox for sure. Solvents typically not. PFAS I do for top assays. Top assays, you're looking at, are you getting a 2 to 3 times increase? And then it's all about, you want to get a magnitude difference between the original sample and the sample plus what came out of the top assay. And I definitely use arithmetic scale for that. And then small sites, if you have 0 to 100 nanogram per liter PFAS, just keep it at an arithmetic scale. It is easier to visualize changes spatially. You only use log scale when you've got many orders of magnitude that you have to try and make sense of.
Okay, great. Another question. What's the largest number of PFAS species you would typically include in a stacked bar map?
It's not 20 and it's not 40. So I've seen a lot of stacked bars, especially with top assays. The trend initially was, let's just show them all. And that's too much. I'll show up to 9 or 10. My biggest number of chemicals is the 3 main sulfonates, the carboxylates, PFBA to PFOA, maybe PFNA if it's regulated. And then usually I'm starting to show now 6.2 FDS, so you can see where it's changing. But that's kind of the limit because people have to remember what colors are associated with each chemical in the bar. I do think the key is if you have 3 groups you're showing in a stack bar, use 3 main colors and just have different shades of them for different chemicals. And then people really just need to remember sometimes 3 colors for 3 groups instead of 9 or 10 colors, which is a lot more complicated.
Great. And Grant, I have a question for you. We see a lot of these radial diagrams used in non-PFAS type characterization. So can I assume this is being used outside of just PFAS characterization as well?
Oh yeah, completely. I mean, I actually developed a radial diagram tool in 1999 for chlorinated solvents, hydrocarbons, redox indicators, looking at lines of evidence for M&A. So I'd say definitely chlorinated solvents. You've got parent species, daughter products. You want to look at ratios between them, at locations, between flow locations on a flow path. So it's metals, same thing. So yeah, definitely a lot of applications. We call it, initially I was going to call it visual chem, so people wouldn't be too focused on PFAS, but it really is focused on PFAS right now, but it applies the same tool, can be used to look at solvents, hydrocarbons, right from taking the software out of the box. It's very easy.
That's perfect. Excellent. Yeah, that's kind of what I thought. When you look at the radial diagrams, you see that a lot in aqueous geochemistry and such things. So very innovative. I like how the graphs are put on a map so you can have spatial orientation. So very well done. And Grant, I think we've reached our surpassed our time limit here. So I don't think we have any other questions. If you do, you've got Grant's email. So thanks again, everyone. Have a great rest of your day.
Thanks a lot, everyone. Thanks for your attention.